I want to thank you for joining us for the webinar today for managing a successful oil analysis program. We are on the hour, so we are going to go ahead and get started with a little bit of housekeeping first. If you have any questions, you are welcome to add them in the questions area or the chat, and we'll be happy to have them answered towards the end of the presentation. And if you do run into any technical difficulties, you can also mention that in the chat, and I can help you out privately if you run into any issues there. On that note, I would like to present Evan Zabowski. He has been with Testoil for many years at this point, and he trains many of our customers in a variety of different fields, including lubrication fundamentals, contamination control, condition monitoring, RCM, FMEA, and used oil analysis. And training is often geared towards the CLS and OMA 1 certifications from STLE, as well as the MLA and MLT certifications from ICML. Evan is a CLS, or a Certified Lubrication Specialist, who also holds certifications for OMA 1, MLT 1, and MLA 2. And his many professional achievements include significant contributions to STLE, such as being the editor of TLT in 2009 and still serving in that capacity. He's also been nominated to STLE's prestigious board of directors. Evan's been a key member of STLE now for over 20 years, donating his time to serve as chair of the Alberta, Canada section for 8 years, and also as an instructor of the condition monitoring course at the STLE annual meetings. He's also served as the editor of the STLE Alberta section's Basic Handbook of Lubrication, 3rd edition, and is the contributing editor for STLE and CRC's Handbook of Lubrication and Tribology, Volume 2, Theory and Design, the 2nd edition. Evan also volunteers on 15 different ASTM committees, which allows him to vote on updates to various standards and methods, as well as ASTM at large and API. At Testoil, Evan's customer service objective is to offer remarkable assistance in every possible way in order to ensure our customers are satisfied. And to that end, Evan leverages his outstanding industry credentials at Testoil every day, and you all are going to get to experience that today. So Evan, without further ado, I am going to pass the controls over to you here, and we can go ahead and begin the presentation with your slides.
Great, thank you. All right, there we go. So yes, successful program. So essentially this presentation I've broken out into 6 essential steps. We're going to follow the W's and an H if you're familiar with the who, what, when, where, and why, plus how. We'll just reorder them a little bit. So we'll start off with the why. Why are we going to have a lubricant analysis program? That's key. But then we'll move into the who is part of our team, then what machines we're to take samples from and collect data on. When does the program begin? Where are the pitfalls? And then finally, we'll answer that question of how is the program performing? Is it meeting our goals, and review all that. So with those 6 steps in mind, let's just dive right in. Step 1 here, the who. Who should be involved is partly driven by the why we're going to have a program. So when you think about the why do you have a program, you have to have some sort of benefit that you're going for. Otherwise, why would you do it, right? So the basic ones, there's sort of 3 common reasons to do an oil analysis program. And the number 1 reason, one of the lowest hanging fruits as we call it, is to extend drain intervals. That can be an initial savings on spending money on oil and disposal, and the labor, of course, is to look about the lubricant's condition itself, whether it be for particulate, moisture, or even acids, and trying to extend the life of the lubricant, but in conjunction, increase the performance of the machine. Another reason is to decrease the amount of work orders that get opened, and number of times the machine is shut down for routine inspections or any minor causing downtime. Another big one is just overall length of service for the machine before it's ultimately replaced or completely overhauled, so you consider it that way. But one of the ones I like to point out that I think is very important is when you do any form of condition monitoring, not just oil, but whether it's vibration thermography or even infrared, what you're really trying to do is be predictive. So you're going to aim to reduce the severity of a failure. You may not prevent the failure, because if something's going to fail, it will probably fail anyways. But if you can catch it sooner and take corrective actions earlier, the severity of that failure should be significantly reduced. The last one, though, is that, and you'll see kind of where this is going, reducing the severity, but we want
Evan,
to
you
know we're
seem to
doing
be
things
cutting.
with a purpose and a
Evan, you seem
plan,
to
and
be
not
cutting in
simply,
and out a little.
oh,
I don't know if you want to try maybe turning off your
okay,
video too, so you're not using as much of the bandwidth for that.
all right, let's try that then.
All right.
Here we go. We'll see if that improves things. But anyways, I was just finishing up with, we're trying to not use alarms as a reason to do things, right? We don't want to wait for the failure to occur or for it to at least enter into failure mode. We want to be as predictive as possible and do things on as much of a schedule with as much pre-planning as possible. It helps reduce costs, it helps reduce downtime, and of course, therefore increases uptime. So with that, I mean, you have to pick at least one of these reasons to have an oil analysis program. They help form the goal for the program. Now, when we talk about this, like I said, there has to be a benefit. So in picking one of these, we need to, generally speaking, an economic return on investment, that we will have a savings with all these costs. And if you look at various examples that are out there, and I'll go through a few at the end, they range anywhere from 2.5 times return on investment to a 20 times return on investment. Point simply being, it should pay for itself. And the idea why that is that if you look at different statistics, they all hover around the majority, whether you want to believe 80% or 90%, but the majority of failures have something to do with the lubricant or its condition from degradation. Lubricant analysis picks up on contamination and degradation quite easily, so this helps us identify some of the more common problems that we could find leading to an equipment failure. Another reason to have a lubricant analysis program is it will support root cause analysis investigations, or if you prefer the acronym, failure modes effects analysis. And it also works with synergy, meaning sort of a double positive effect here with the other condition monitoring technologies, especially like vibration. As I said, we have to pick a goal, to have a reason for doing this, and we need to make sure it's going to be economically feasible. So the three most common that get chosen are that first one I mentioned. We want to reduce our oil consumption. So that will help us understand what we're testing, which properties of the lubricant. Common one is extending equipment life, which in this case we'd focus more on, say, wear metals and contaminants. And of course, another good one is just to increase the overall reliability or uptime. And we might do a bit of a balance between those first two. So knowing why we have a program, knowing what the goal is going forward, we can now form our team of who's going to help us get there. So generally speaking, when you look at personnel required to be part of this team, you need to make sure they have the right skill set. I mean, that's true of any team. So it starts with something as simple as pulling samples. If you can't get somebody who will pull samples in a consistent manner from a consistent location, you're going to get very noisy data coming in, and the program will already begin to fail before you've even really gotten started. So it seems like a pretty simple thing, but that's one of the skills you need. Similarly, we'd need the skill for interpreting the reports. We need the skill in acting on any action items. I mean, there's a lot to that skill statement. Another aspect, time. The personnel that we choose to do this must have the time to do the job properly. It's very common in some facilities to saddle attrition, as an example, with oil sampling or condition monitoring, simply because they know they visit every machine regularly. And that may be fair if they've got the time, but if they're already pretty much dealing with a full slate and you have them running around doing these extra tasks, well, either shortcuts will take place, or some will get missed. So we want to make sure that they have time to do that side of the job correctly. And the example I give here is the time to read the reports. I mean, it's an all too common aspect that many people can find the resources to pull samples, send them to the lab, pay for the results, but by the time the reports come back, nothing is being done. We don't have people reading the reports and writing up work orders based on the reports. They more or less glance at them quickly and say, yes, it looks like it will still run, we'll just leave it. And they're not trying to predict anything, they're just looking for the absolute catastrophic bad examples to say, okay, maybe I should do something now. And at that point, it can be too late. Another aspect is drive, meaning motivation. They have to care about the program, they have to want it to succeed. Passion goes a long ways when it comes to the right personnel. And part of that, as I always say, culture change may be required because having the right passion without the ability to act on it, or having to deal with other people who are just not as passionate but are in a higher position and can control what you're able to do, that can kill the program before it gets started. So those are the ground personnel, if you will, the ones actually out there pulling samples, generally speaking, the ones reading the reports, the ones writing up the work orders. Another part of the team, though, is you should have somebody who's like a champion, somebody who's done this before, perhaps, is always good, but somebody who is in a position to make things happen if they need to, right? They can motivate the personnel below them, but they have the authority to make others, act in compliance. It's one thing to have people in charge of an oil analysis program to say, go pull samples, go read reports, but if they have to report to operations, to be able to access the equipment or to be able to shut it down, to do some preventive maintenance, and they're not being allowed, you need that champion who's in a high enough position to be able to at least speak to, maybe the operator's boss and say, hey, we got to make this happen. And last but not least, another good person to add to your team, if you can, is a mentor. Somebody who maybe doesn't even work at that facility. It could be third-party contractor sometimes, but often you can find them at sister facilities or else high up in your own organization. But there's somebody who's probably done this before, seen it done before anyways, even if they weren't the ones responsible for it. But they've got a track record and they will support your efforts. So if you have questions, if you need some insight and guidance as to how to do things a bit differently, this is the kind of person you can go to. But they're not part of the hierarchy, the chain of command, if you will, to your organization as it relates to the program. There's somebody outside of this who, basically is non-biased at this point, but just pro oil analysis. So once you know why, once you have who, now you need a plan. So the plan usually centers what machines are you going to pull samples from. And to get to that point involves performing an audit, and an audit has all these steps involved in them. So let's go through the steps to understand what I mean by them. So when you do an audit, and again, this is done all internally, you don't necessarily have to contract this out, you can do this yourself. You start by reviewing your storage and handling practices. Look for some of those easy changes you can make to improve the quality of your lubricants going into the machines, improve the accuracy of which lubricants going into which machine, things like this. So you start with rate from delivery. Where do you put your new oils? What kind of housekeeping do you have? What kind of filtration do you have? See if there's improvements that can be made there. Look for ways to prevent contamination, right? Proper breathers is a very common thing that can be upgraded on both the new lubricant storage and even on the machines. Make sure you consider if you need desiccant though. That's not required by all people in all areas. It handles humidity. So unless you have a humidity issue, you don't necessarily need to go all the way to a desiccant breather. But if you do require it, make sure you size it appropriately so that it has the ability to strip enough moisture to make the difference. But once you do that kind of audit, on the lubricant side, then you go up to the machine side, and now you need to select which machines you want to sample. And there's essentially 6 factors that I consider to make it worthwhile sampling. So one factor is criticality. If the machinery is critical to your overall operations, it is worth sampling. Generally, when we say something is critical, means that it doesn't have a redundant capability. There's not a second one that takes over if the first one fails. Or we mean that it has a cascading effect on other lubricated components. So if it shuts, other things shut, other things trip, that kind of thing. Second aspect is if it's designed for safety. Is it required to provide some sort of safety function, a rollback device on a conveyor belt, a braking system on an elevator, and of course, fire water systems that are quite common in many, many plant facilities. If it's a requirement for safety or any other regulatory concerns, right, it is worth sampling. Third aspect is expense. Is it costly to your company when something happens to this? You look at that picture there and you see a $3 million dump truck. That's pretty expensive. But on the other hand, the shovel that's filling the dump truck beside it is also, not only more expensive, but if your shovel doesn't work, you're not filling trucks. So it doesn't matter how many $3 million trucks you own if there's no way of filling them. So the downtime expense of something like a shovel at a mine is incredible because it essentially shuts down the greater part of the mine. So that's what we mean by expensive. It doesn't matter if it's expensive to replace, it could just be expensive to the operation of the facility. Fourth one is reliability. If it does not have a predictable lifespan or failure, if things just happen, you don't seem to have logical explanations for them or any sort of predictable pattern to it, you probably should consider implementing lube oil analysis on it. But if you have machinery that's designed for a service life of 5 years and you easily get more than 5 years out of it, it's one of those things where we'd sort of look at it and say, why would you bother sampling it then? You're getting what you need out of it, so focus your efforts somewhere else. The fifth is if it operates in an environment that you would suspect would contribute significant contaminants to the machinery. So it could be humidity, could be particulate, could be heat, right? Nearby heat even is considered detrimental to the operation of another piece of equipment. And last but not least is it looking at the expected efficiency, right? Does it seem to be consuming a bit more power? Is it not producing the widgets or operating at the speed you think it should? Anything like this that would suggest to you that it could be better, that would be a reason to sample it. So any of those 6 reasons is a reason to take samples from that piece of machinery. But if you look around your facility and you go through this checklist of 6 things and cannot apply it at all to a particular piece of equipment, ask yourself, why are we even going to bother sampling it then? Right? It maybe is not required. And again, we should probably focus our efforts on the ones that matter the most. Now, once we decide that it is worth sampling, we have to decide where to sample it. So we always want to make sure that the sample point gives us a good idea of what's going on inside. So we typically look for live zones, not dead legs. We want good circulating hot oil that represents exactly what's going on in the machine. And when we pick it, we want to make sure that it's a choice that will allow us to take the sample consistently. Same spot, same procedure every time, we'll get trendable data. But if you're asking people to just shove a hose in through an opening and you have no idea where that hose is going to go, left, right, to the bottom, that adds noise to the data and can make it a bit more difficult to collect that kind of information. Once we decide where we're going to sample it, we have to decide what testing we want. And that is partly driven by the machine type, right? Different machines have different wear modes or degradation properties. So you can choose testing to best reflect those. You also want to consider the fluid type because different types of synthetics may have different properties you should pay particular attention to, right? Some oils are a lot more sensitive to water, as an example. So you might want to consistently monitor water content. Operating conditions is another factor. If you know you've got a known contaminant getting in there, you should probably monitor that. And again, we're going to circle all the way back to the beginning. What was the program goal? Right? Were we trying to extend drain intervals? We'll focus on fluid properties. Were we trying to extend rebuild time or equipment life? We'll focus on wear modes. Are we looking at uptime and reliability? Well, we might want to focus on both then. But other things that we should consider is then how often should we sample and do those particular tests? And the frequency is most affected by some of those same factors. Again, the criticality and the expense will tell us to sample a bit more frequently. If there's a reliability issue or a harsh environment or any operating conditions that are an extreme, we'll probably want to sample it a bit more frequently. So lots of factors go into these decisions in terms of pulling a sample, deciding what test to get and how often you're going to want that piece of data. Even if you decide to sample something as frequently as monthly or quarterly, it doesn't necessarily mean you always want every single result at every single sample. There are some types of results you only need, every second or third or fourth sample. But last but not least, as part of all this, we're talking about pulling samples and picking tests and how often we want it to be done. Ultimately, you need to decide where are you even going to send these samples. So picking a lab is a big consideration as part of your oil analysis program as well. And that falls into a number of factors here. So the big things that I always consider worthwhile investigating is how fast can the lab turn this around? How good are the analysts doing the interpretation? It's one thing to get accurate numbers out of a lab. It's another thing to get a solid interpretation of those numbers. One of the factors we can use to sort of verify that the lab should be accurate, though, is any certification. How deep does the interpretation go? Is it just reporting of numbers with a couple of graphs, or do they actually write you up a little bit of something? Do they show things in correlation with other things? And just overall, what is the readability of that report? Can you actually pick one up and get the information out of it in a short period of time? Or are you basically scratching your head and wondering what you're looking at? So when it comes to the labs to choose from, there's essentially 4 choices. And I just want to quickly run through some advantages and disadvantages of the 4 choices. So we'll start with OEMs. Some of you may deal with the equipment manufacturers have a preferred lab or their own lab, and they have basically what we call a branded program that runs through them. Lubricant suppliers often partner with labs and again have a branded program with their name on it. There are independent third-party commercial labs, much like Test Oil. There's a few of us out there. And then some people just choose to do it themselves. They want an in-house lab, and they look at staying in control of all the variables that way. So here's a quick rundown of just the 4 choices. When you think about using an OEM, the advantage is they have definitely targeted knowledge on your equipment. It's mostly there to provide warranty support, and often this work is done at either no charge or it's part of your program, part of your warranty program. The downside is that if you own a mixed fleet of, whether it be pumps or engines or whatever it is, they don't have experience with the rest of your fleet. So you either may have to run more than one program or just suffer that part of your fleet can't be treated the same way as the rest of your fleet. Another big disadvantage that not everyone considers is, remember, they have a vested interest in selling you parts and service. So when you get a report back from them and it suggests to you that something needs to be done, how confident are you that they're acting in your best interest, that's saying this definitely needs to be done? Or how much do you think they're just saying it because they think they can sell it to you and they make money off of it, right? It's the whole argument we have if we take our car in for an oil change and they tell us we need new brake pads without providing us the data behind that, right? They need to tell us that, yes, your brake pads are worn, they can show them to us, we can see this, and we go, okay, yes, definitely they need to be replaced. Whereas if they just tell you something and say, yeah, we think your pads need to be replaced without any data behind it, you're wondering about it, right? So it's that kind of mentality. The other aspect, though, is that often because of their focus, the program may be quite simple. It doesn't get into a lot of depth regarding, say, fluid conditions, as an example. So then people look toward a lubricant supplier, which is kind of then focused on the lubricant itself. And sometimes they can liaise with your OEM, so that could be a good thing. And again, often you don't have to pay for the program. It's just built into your oil price. But the downside, again, is similar. They don't have experience with other brands of lubricants. So if you're not using them as your exclusive sole distributor of lubricants, well, again, there may be some things you can't have treated the same way. Now, they have a vested interest in selling you more oil. So when their report comes back and it says the fluid needs to be changed, does it? Or can it be recovered or saved, or can you just do some top up and get back to where you need to be? The other thing, again, is their program may be overly simplified because they're trying to keep their costs low because Again, whether it's an OEM or lubricant supplier, they're footing the bill. They may be passing it on to you a little bit, but they generally aim to keep the program fairly inexpensive. So where a lot of people look to then is a third-party commercial lab. And the advantages is they've got experience in all OEMs, all lubricant types. They have no vested interest in selling you parts or service. So when they give you an interpretation that says, we think this needs to be replaced, they're not going to make a buck off of it later. Nice thing too is you can customize what they do. They allow choices to be made. You can supplement your testing, augment your testing, whatever you want. It's open because, well, you're now the customer, you're paying for it. The disadvantages are that sometimes with these labs that we can consider them to be, jack of all trades, master of none. Some of them have very vague recommendations because they just don't have the expertise to be terribly specific. And of course, like I said, at this point, you're probably paying for it, so there's no way to get this one for free. Costs will run higher depending on the level of service you require. Now, the point of this presentation is to show you it should still pay for itself, but you need to be aware this is one of the more expensive ways of doing things. The last choice is to do it in-house, do it yourself. And the idea behind this is that you're only analyzing your own samples, so you tend to focus your expertise on your own equipment and you get quite good at this. Generally speaking, depending on who you're used to dealing with and how fast you normally get results, doing it in-house is typically faster. And the nice part of it is the end user then is in control of everything. If they want an additional test, they can get an additional test. They want it tested a certain method, they can do it that way. I also list that as a disadvantage. Now they're responsible for having all the equipment, having all the capability, having all the staff, training the staff, all these other things that you don't really realize is one of the reasons you pay for a contractor to do it. When you contract out work, what you're paying for is the ability that somebody will always be there to do it for you. So that's why I listed the disadvantages that can be a lot more difficult to build up staff expertise. Right? You're not realizing that when a lab's been in business for a number of years, they've got experienced personnel there and have an in-house training program to keep that level of training up. The other aspect is because you have to outlay money for all the equipment up front, your initial cost will be very, very high. Now, once it's running, your cost may be lower than what it would cost to send it to a lab, but at first, you could easily be spending $250,000 getting all the lab equipment and an appropriate space set up to be able to do your own in-house oil analysis program if you want to have a fairly full slate of tests done. I mean, obviously there's ways to buy mini labs and do it much cheaper, but I'm trying to keep everything on sort of an even comparison here. Now, when you're evaluating what type of to use, here's a few of the considerations I say to keep an eye out for. As I mentioned, the first one was accreditations. For what certifications they have. ISO 9001 simply means they have documented processes. It doesn't mean they're good, just means they're documented. ISO 17025 means they've been audited, that they have to adhere to third-party independently reviewed standards, namely things like ASTM and ISO. Look for the certification of their own personnel, the people doing your analysis and the interpretations. Are they certified? OMA1 is a good one, CLS is even better. Also look for experience. Do they have experience in your field, right? It's one thing to be a power plant, but if you send your samples to a lab that specializes in mining customers, they might not know the intricacies of your hydraulic control system, as an example. What kind of testing they offer. When they give you a test slate, do they just offer some standard packages and that's it? Do they offer exception testing, meaning if you get one result that's high, they automatically follow up with another test to confirm it or otherwise quantify it? And the best choices, are they flexible with what they can do? Are they willing to tailor their testing to your requirements, your requests? Another consideration is the test methods themselves. Now, if you undergo an ISO certification, you would already know this, but if it's just a 9001, you have to ask, what kind of procedures are you following? ASTM and ISO standards are great, but as you're going to find, if you deal with commercial labs, oftentimes we go to modified methods. And the reason for the modifications are generally to save time or money because of the quantity that has to be done and the time frame they have to be done in. But when you just modify the method for your own reasons, it can have an effect on the test, and this may not be necessarily positive to the end user. When you do this through an ISO 17025 accredited system, we have to verify that the accuracy of the test, meaning the precision and bias, or what you would call repeatability and reproducibility, are unaffected, that they comply to the existing standard as it is written. So always ask questions when you see modified methods. You want to make sure that they've actually verified this and they're not just shortcutting it, like I said, for their own reasons. Next, start looking into the logistics. The first one on that side of the equation, I list turnaround time. We know that we can ship stuff overnight pretty much anywhere within the country. There's no reason we can't get the samples to the lab quickly, but we now depend on the lab to get the results back to us quickly. So generally speaking, most labs should be able to turn around the results in 24 to 48 hours, and that's from time of shipment to the lab to time of receipt, getting the results to you. So that's not time at the lab only, that's time including the shipping times. We also want to know, how do they alert us when there's a problem, right? Do they just PDF the reports and send you all the reports and you have to sift through them? Do they highlight the ones that have problems? Do they allow for web-based notifications? Is even better, so you can actually log into a website and see the worst ones sorted to the top and all this kind of stuff. So there's lots of ways to handle that side of the delivery. Next is the quality of interpretation, right? Do they just use limits? That's it, stats, and if it gets an alarm or doesn't get an alarm, do they statistically derive their limits to tailor them to your exact make, model, and maybe even oil combinations? Better yet, do they use trends? And deviations from trends can be far more valuable than just static limits. Or can they combine the two and show you the advantages of trending and knowing some limits being statistically derived? So there's, again, different ways of doing this, and that generally is considered among the best. Towards the end, though, once they've looked at your report, set off some alarms, how do they write up the interpretation? Do they give you very generic statements that just simply says stuff like, iron is high, look for sources of iron? I mean, that's not helpful. Do they tell you sources of iron may include and give you a few items to perhaps look at that would be common sources of that iron? Or better yet, do they suggest to you that, hey, iron in conjunction with chromium suggests, shaft wear compared to bearing wear or something along those lines? So there's lots of different ways they can write up their comments, and that is part of that deliverable, part of that report. You also want it to be very readable, right? Is it just a bunch of numerical results and you don't know how to make that out? Do they put some graphs in it to give you some ideas of trends? Or do they even provide you with some sort of grading system, show you limits maybe on those graphs to show you how close you are to what's considered versus how far away you are to consider, what might be abnormal. And kind of the last way to look for is, when you look at these reports, can you easily tell what machine it's for? That way you're focusing your thoughts on, okay, what do I know about this machine? Is it easy to find where the most current result is on that report? Is it to the left? Is it to the top? Is it highlighted in a different color? Do they provide you with baseline information so that you have a comparison for that most current result? Do they use any images? Do they take pictures of, say, your ferrographies or your patches so that you can see some of what they saw with that comment that, hey, there's a lot of debris here? Do they provide you the web-based access to all the results? I mean, it's one thing to be sent an email, but you don't want to be sifting through your emails a day or two later when you're looking for something. You want to have a fast way of finding it again. And last but not least, and this is a very small consideration, but when it's important. How long do they hold on to your samples? Right? By the time you get a report, read it, interpret it, send somebody out to go check on something, maybe when they come back with whatever information you sent them to find, that information tells you you should dig a little bit deeper with that sample. So isn't it great if you could just phone the lab up and say, hey, can you pull that sample again and maybe redo this test, or I'd like an additional test run on it and get more information? It would really be detrimental if they tell you, no, we already dumped your sample, send us another one, and you have to wait another 24 to 48 hours for that answer. Better is when they can say, yeah, we'll run it and we'll call you in an hour or two when we've got the results. That'd be great. So just in summary, like I said, when you're picking labs, you want to consider turnaround time. And that's not just how fast the lab does their end of it or how fast you can get it to the lab, it's both. Consider the logistics of how everything's handled. Of course, above all, make sure quality assurance is nice and high, that you've got accurate data to begin with. How do they send the reports out to you? How is that data, disseminated to whoever needs it? Can they share it with your OEMs, your lube suppliers, other people? Can they tell you what test methods? Again, with the modified methods, a lot of people use modified methods, which is not to say they're not good, but you want assurances that it's been verified against a published standard so that you know it's good. Flexible testing, of course, is very beneficial to the customer so they don't have to suffer paying for tests they don't have any interest in those results. Like, why would you get an acid number if you're going to change your oil every 6 months anyways? Right? You're not likely to build up significant degradation products in that 6-month time frame, so perhaps you'd like the option of not paying for that test and maybe focusing on something a bit more pertinent to that particular asset. And last but not least, as I just wrapped up on the previous slide, can they present information to you in a reasonable, technically sound presentation, a report that you can read, you can interpret, you can say, yes, I know how to move forward after having read this. So when I say that, like I said, do consider, once the report's in your hands, how are you evaluating that data? Are you leaving it with just what the lab personnel had to say and you're not moving forward on that? Are you now sending these reports to outside consultants, right? Some people use different firms that offer to do this task for you, that they will take what the lab has produced and then offer up their own interpretation, maybe write up your work orders for you. And other people may use some software. There's what we call an expert system out there. There's many varieties of these that can suck in the data, maybe combine it with other data like say from vibration or other technologies, and make its own comments or recommendations going forward. So there's sort of a little, if you want to call it epilogue to this, that there might be other considerations beyond the lab in terms of what are you doing with that data. But saying that was the third step of the, what machines are going to be analyzed. It's quite an intensive one there. How do you begin? Well, no one's going to say go for it unless you've got proof that it should be done. So you started with a why. You started with a reason for the oil analysis program. You now need to prove it. You need to say to them, oil analysis will achieve this goal. So the easiest way to do this is to balance costs with benefits. So in terms of determining your costs, one of the things I always say is consider not just the ongoing costs. Right? Many people sit there and say, well, I'm going to pay the lab $30 a sample. I'm going to take 100 samples a year. It's a $3,000 a year oil analysis program. No, it isn't. It has a lot more costs, especially at the initial outlay. You're going to have to perhaps install some sample fittings. You're going to have to train your personnel on how to take samples, how to interpret reports. You may require a little bit of consulting, whether it's an audit up front or just some effort as you start receiving your first sets of results and starting to understand how those work. There's a lot of other costs that way. So when you determine these costs, consider more than just whatever's the ongoing cost. When you think about these savings, the benefits, these get a bit harder to quantify, but you have to think about it from multiple perspectives. Right? Are you saving money in terms of uptime or reliability? Are you producing more widgets per hour? Are you just down fewer hours in the year? And then other things is like parts and labor. You're spending less money on oil, but you're spending less money on the time it takes to shut down that machine and change the oil. Are you spending less on parts, right? Are you, maybe it's replacement parts, maybe it's even replacement machines. There's lots of ways of looking at the potential savings, but I always caution people, and you'll see it coming up, be very liberal determining your costs, be very conservative determining your savings, not the other way around. It's better to underestimate your savings and overestimate your costs and be wrong about both, because then it's just all the more beneficial. But if you've underestimated your costs and you've overestimated your savings and you turn out to be wrong, well, then the program doesn't look anywhere near as successful as maybe you touted it to be, and you have the risk of it being canceled. So to that end, where are the pitfalls? Part of the pitfalls come from, and this is why I emphasize in the third step, what machines should you even sample? Because it is not an answer to say every machine with a lubricant. That may be too much. And that's one of the biggest pitfalls with an oil analysis program, is just simply taking on too much. We jokingly call this analysis paralysis. Right? If you take 100 samples today, do you know what happens tomorrow? You get 100 reports. Do you have the capability to go through 100 reports? Right? Maybe you do, maybe you don't, but go through 100 reports is going to take time. Write up work orders for 100 reports will take time. People doing the work on the work orders will take time. Right? This all has to be, sort of thought of, that you have to start, maybe a bit slower than you think, and a bit more focused. Maybe on your top 10 assets at first, not everything in the plant. To that end, I also say expanding too quickly. Sometimes we try it a little bit, it looks great, and then we just implement it across the board, and we don't have the expertise, the training to be able to do all this. And part of that comes down to something as simple as training, right? It's one thing to go out and collect one sample. It's another thing to go out and collect 100 samples, because the different configurations, you may have to have different considerations for how those samples are pulled. If you have one report versus 100 reports, there could be different tests on those reports, different numbers coming back to you. Again, you need to have the training to know how to read these different values from the different tests. All kinds of things like this, like I said, that sort of come into this taking on too much or expanding too quickly, right? Baby steps. You want to start off slow, build momentum as you go. Another big pitfall, though, is related to communication. As anyone will always tell you, right, communication is king. A big part of an oil analysis program failing is about setting expectations. So it's important that everyone's sharing that common goal, right? You need to make sure it's well communicated. If you said we're going to save on oil costs, everybody needs to know that, so they understand why you're doing it and what your hopeful outcome is. You don't want somebody sitting there saying, well, that machine failed anyways, even though you had a loop program. You're like, I wasn't trying to prevent its failure. I can't prevent its failure, maybe as you're thinking. All I can do is try and use as little oil as possible throughout the life of that machine. I can at least save that kind of money. And if people realize, oh, well, that was your goal. Well, how much oil did we use this year compared to last year? And you can show them that it was a savings, the program's still successful. But if people have these, sort of unwritten or non-shared expectations of the program, yeah, they may not feel like your program's working, and they may work either against you or just not be working with you, right? Not rowing in the same direction. And that's why I always emphasize the culture change. Right? People need to see the benefit, and they will only see the benefit if the program's working towards a set goal and people know what that goal is. Otherwise, they will assume the goals, which may not be achieved by the program, and therefore it may look like the program is failing. But the last side of it comes down to the how. So we need to understand that with this communication, it's from the top to the bottom, from the bottom to the top, everyone's involved. And we know what the goal is. We know if we're working towards the goal. We need to know then, now step 6, how are we measuring that goal? Right? If we set out to do something, we need to have a way of measuring it. Right? It's one of the common statements: if you don't measure it, you can't improve it. So if you can't improve it, then why are we doing it? So the most common methods for measuring things is to use what we call KPIs, key performance indicators. Most common KPIs are just, counts. How many work orders did we create? How many work orders were completed? How much oil was purchased? How much oil was consumed? Things like this. And if we can track the changes that are related to those and just show from one quarter to another quarter, or 1 year to another year, you can have that proof in just easy black and white figures to say, yes, we spent less money doing this, or we spent less time doing this, and that's a savings. You can come up with a way of quantifying it as a savings to show the program's doing what it's set up. Suggest that it's done annually, mostly because you can't review it too frequently, because there may be month-to-month, quarter-to-quarter fluctuations, but you also shouldn't let it run for several years.
Hi, Evan, can you hear me? It seems like we might have lost you. Let's see here.
There we
Hi,
go.
Evan.
I
Oh,
was
you're
showing my
still,
audio.
Evan, your audio is still cutting it out a little bit.
Hey, but can you hear me well now?
Yes.
All right. Because yeah, it showed the connection was completely lost there for a second. Um, Anywho, but why we continuously do these evaluations is to show we're still working in the right direction. And the easy answers, like I said, are counting, just counting work orders, oil changes, oil volumes, uptime hours. Those are some relatively easy KPIs. I'd just like to show you a bit of an example of a deeper one. It's a data mining one, and this is coming from a mining customer, so apologize to anyone who doesn't have experience with mobile fleets, but you can maybe see the value is applied to any fleet. In this example, on the left-hand pie chart, we just observed how many samples did they pull from what type of machine. So like I said, that could apply to any type of organization. Over on the right, though, they looked at their alarms and they said how many of their water alarms, like high water content, come from which type of machine. And the two values I want to show you are these apparent discrepancies, that there are fewer final drive samples than there are engine samples, but there's a lot more water alarms on a final drive than there are an engine, right? Now that sort of disproportionality may seem like there's a problem with final drives in that they have a lot more water issues than an engine does, but can you explain why an engine has so few water problems? Well, an easy answer is that engines operate at an elevated temperature because of the combustion. Therefore, they should be able to drive off some of their water. So it might make sense that the engines don't have as many water alarms as they are proportionate to how many samples are being pulled, right? You might be able to explain part of it that way. But if we now take the same pie chart on the left and look at the viscosity alarms, and realize that again we see that disproportionality, that there's more viscosity alarms on a final drive than there are number of samples taken for a final drive, we start to balance that and go, well, it had more water issues too. Would water content cause viscosity alarms? And you start to realize those two are related. So really, if you'd like to decrease the number of alarms that you have in your program, one of the biggest slices of alarms comes from final drives, and one of the biggest reasons for that is water content within the final drives. So if you can find a way to help keep the final drives drier, maybe check sort of the seals on these pieces of equipment, and maybe discourage operations from driving through deep puddles, you could eliminate some of the water alarms, which would therefore also drive the viscosity alarms, and your overall number of alarms goes down significantly. And really, you haven't done much different, but you can take away the focus on something that's easy to fix and look for the things that are going to be a bit more complex. So that's why they get into in terms of data mining is sort of looking for these opportunities to help reduce some of the effort and work towards the goals that we set. Right? We could start changing the fluid more frequently in the final drives to help prevent the buildup of water. But if our goal was to reduce oil consumption, right, that's going to work against that. So we need to find alternate solutions. But just to give you other ways that programs have been evaluated, I'll show you a pulp mill. So this pulp mill had 65 process pumps. They analyzed their own samples with an in-house laboratory. They used a particle counter with a limit of 1815 as a particle count, and they did a crackle test to just confirm the presence of water. And again, they don't want any presence. So when they started off on their program, they found that about 70% of their samples failed at least one of these two tests. So what they decided to do was to implement more frequent oil changes, and they set the target one ISO code lower. The outcome was that they had a reduction in the number of samples that failed either particle count or crackle. So they decided to start doing them even more frequently, but keep the target the same, And what they experienced was increase now in the number of faults. So if you can see this, obviously they need to try something different. And the next step, well, it wasn't going to be more oil changes. That was not the answer. So what they looked at then was filtration. Could they filter the oils instead of changing the oils while they were in the machine? Well, when they tried this, they found only 18% of their samples failed. But when they looked closely at the 18%, they found most of them were failing because of water, not because of particle count. So then what they did is they modified their auto oilers to have a tube connecting the oiler to the breather of the bearing housings on these pumps. Therefore, it wasn't exchanging air with the outside environment as the oiler replenished the oil supply. What they then found is only 2% of their samples failed a crackle test, and they were able to set their ISO code limit one code lower yet. And remember, that was in comparison of 70% failing 2 codes higher. So by implementing filter carts and modifying their oilers, they took the number of alarms they had in terms of 70% of the samples pulled had an alarm down to 2% of the samples they pulled had an alarm. Right? So there's proof in the pudding that they could reduce the number of alarms, which meant the lubricant quality, I should say, had been improved, which should therefore have a positive effect on the machine as well. So a couple quick examples just to show you. As I said before, we often track the success of the program based on goals, but another way we do it is based on return on investment. Did we save money? So it comes down to money. Well, as I said before, be liberal with the cost, be conservative with the savings, and one of the biggest factors I point out is don't double dip. What I mean by this is sometimes people catch a problem and they say, wow, we caught this problem. Had we not caught this problem, that machine would have failed. That's a $50,000 machine. Well, that's fair. But then later in the same year, they catch another fault and they say, oh, we caught another fault, and had it progressed, it would have failed. So they rack up another $50,000 savings. Point is, think of it this way. Had the first fault actually caused a failure, you would have replaced the machine for $50,000. You would have had a brand new machine. It probably wouldn't have failed that time, right? But because you're jollying along an older machine, it may have multiple faults, multiple trips, and you can't write off the entire cost of the machine every time you find one, right? That's what I mean by double dipping. And some people are just trying to boost their numbers too much, and it doesn't work in your favor. It makes the program look unbelievably profitable, which cannot be maintained over a long period of time. So be conservative. If you save a machine once, you can attribute the entire cost of the machine if you feel that's necessary. But if you save it a second time, you're going to have to take a percentage of that. You're going to have to say to yourself, yeah, it probably wouldn't be an outright savings the second time because of, like I said, you would have replaced it the first time. Say be very liberal with your costs. When you start saying something like, we're going to reduce the amount of money we spend on oil changes, right? A lot of people look at that and say, well, that math is easy. How much did the oil cost? How much did the labor cost to change the oil? An excellent magazine article pointed out that the perceived cost of an oil change with the actual cost of oil change are quite a bit different. The actual cost of an oil change, now I know you might look down that list and think, oh my goodness, that looks like government spending or whatever, but they're actually, it's very conservative. If you read down some of these, you'll look at, they only took percentages or factors of existing costs. So, when they said oil costs money to dispose of in number 6, they only said that, 50 cents a gallon, right? It's not expensive. When they look at some of the other things, they just said, let's take 1.5 times this hourly rate or 2 times that. And very conservative, I think, in my estimation, but they point out that if you say you want to buy a pail of oil, and most organizations, to say I want a pail of oil means you have to go through purchasing. Purchasing then has to contact a supplier. The supplier has to be issued a PO. That step right there, statistically I've read, costs anywhere from $50 to $100, right? Just to get your organization to cut a PO. Now, when the distributor sends you that pail of oil, they're also going to send you a bill at some point. And again, the bill gets received, it gets put through, accounts receivable. A check has to be cut to pay for it. It has to be mailed out and be processed. And again, it can cost you $50 to pay for something. So you start adding these kinds of things up, and it's no wonder that something as simple as an oil change can cost upwards of, in this example here, close to $1,000 by the time you factor in everybody who handled that oil coming in, going out, the purchase of it, the disposal of it, all the labor at every single step along the way. So be liberal with your costs. It will still come out in your favor. Just to show you how it comes out, a few quick examples here. This is a very old one from the Air Force. If you do the math on this, you'll see why I say, it's a bit conservative. So they did nearly 1 million samples. The program cost $5 million. So if you're doing your math, that tells you they paid $5 a sample roughly. Out of those nearly 1 million samples, they only found 190 that said there were wear-related failures. Right? So think about that, 1 million samples and less than 200 truly indicated a fault. Right? That's a lot of normal-looking samples that you had to go through before you found these particular 200. Now, of those less than 200, only 5 of them did they feel actually averted a failure. So it seems like that's not very good return on your investment when you look at it this far, because you're going, wow, 1 million samples to find 5 faults. That seems like a lot of effort for not much payback. However, these aircraft, as you may be familiar, an F-16 single engine aircraft. If you fail the engine, aircraft doesn't fly. So it may not be able to complete a mission. It may not return to base even, right? So when they did the math on this, the estimate that they had about $15 million in engine repairs. So if you look at a $5 million cost of program with a $15 million savings, right, that paid for itself. If you think about it, from the terms of, even if you just saved one aircraft from crashing, which would be over $100 million, right, that's even bigger savings. The math, and again, how they chose to look at it was the bigger number. That's a 20-to-1 return on investment. That's fantastic. Okay. Realistic Palo Verde nuclear station, they did a joint oil analysis and vibration program. So we've got 2 different technologies being implemented here, but it cost them a little over $500,000 to get the program up and running. Within 1 year, they could document, not just estimate, but document $3.7 million in savings. So you do the math on that one, it's about a 6.5-to-1 return on investment. Again, it still pays for itself. And going back to the Miller Western case study that I showed you, the pulp mill, you got some numbers here, but basically they were spending $10 million a year on repairs and maintenance. They were producing 650 average daily metric tons per day. 6 years later, they'd increased their output to 800 tons per day. They'd reduced their repairs and maintenance budget by about $1 million a year. And it was little things like this. They had, these rotor drive, these big gearboxes that would last 2.5 years. The rebuilds were expensive. The downtime was costly. Again, like the process pumps, they put filtration units on them. They set an aggressive target. At the end of 6 years, they avoided many rebuilds, 6 of them, coupled with 108 hours of downtime. So the initial outlay for the filter carts was about $22,000. To run the filter carts through the 6 years was about $20,000. But just in the costs alone, in terms of rebuild, they avoided $120,000 worth of costs. So you're looking at a 3-to-1 return on investment there, and you haven't even counted the 108 hours of downtime. So the last thing I want to leave you with is, how can you come up with your own numbers, right? It's easy when you have something very tangible that you can document that says, here's a thing, here's a cost, here's a savings, do the math. What if you're just trying to estimate it? What if you're just trying to come up with reasonable numbers? So the last example I'll walk you through is from this excellent magazine article. And it says, look, classify your failures in 3 categories: severe, moderate, and minor. Come up with a cost for the downtime, for the parts, for the labor, so you can come up with a total, raw total cost. Right? Now, from there, doing what you're doing right now with no oil analysis program already going, estimate some probabilities. What's the chance a failure is going to fall into which category? Then you end up with a weighted cost. Now, make a very conservative estimate. With your oil analysis, imagine shifting some of the severe failures to being just moderate failures, and some of the moderate failures to being just minor failures. So all you're going to do now is change those percentages a little bit, right? So you're shifting some of them from one category to the next to the next. Now your weighted costs go down significantly, and ultimately the math works out that every time you have an event that you can catch with oil analysis, there's a potential savings there. So it's a neat way of estimating it. You can play around with the numbers to your content. Right? You can do as little as a 10% change. So take 20% of severe failures and bring it down to 18%. Right? Take 30% and bring it down to 27%. And then take that 5% and add it to the 50 and call it 55%. Even simple changes like that is very impressive how much money you can look at savings. So understand, like I said, it's the 5 W's and an H, just kind of reordered. You have to decide why you're going to do this, who you're going to have helping you achieve it. Create a plan, though. That's the what. What are we analyzing? What are we testing? How often? All those kinds of questions get answered. When do you get to start the program? Only once you can prove that it should be able to save money. The pitfalls, where are the pitfalls? Remember, communication and start slow. That's the big thing. And last but not least, as we just finished up there with, constantly go back and look and see, are you achieving the goals? There's no point doing what you're doing if it didn't achieve the goal. Either change the goal or change how you're doing it to work towards that goal. So with that got us through the 6 steps, only a minute over the hour. So I'll thank you so much for listening to us. If you have any questions, I guess we can take a couple now, but again, thank you for listening and hope you got something out of it.
Yes, thank you, Evan. That was great. We do actually have quite a few questions. I will just pick 2 or 3 though for us to actually go through live, and then I know you'll be able to get back to everyone after the fact later today.
Sure.
One of the questions that we have is, based on the equipment make and model, do you recommend the customer to change or switch to another type or quality of oil? So, for example, instead of a mineral, switch to a synthetic. And they put as an example, in the case of HDEO, from a 15W40 to 10W30 or higher API oil. I think that's kind of a loaded question, which is why I brought this one up, because there are a lot of different factors involved with making the switch between oil.
Yeah, the short answer would be not based on make model would we make a kind of recommendation like that. It would be based on conditions. So yeah, if we found that the oil was not standing up to it as a mineral oil, there may be a suggestion to move towards a synthetic. But generally speaking, it's probably more the end user discussing with their lubricant supplier about the conditions that they're going to operate the engine under to suggest whether or not a synthetic is required. But part of the shortest end that you can get is how often do you plan on changing it? And there's no point switching to a synthetic if you're doing schedule-based changes that say every 500 hours you're going to drop the oil, because you're not going to receive enough benefit from the synthetic to warrant the cost increase. But if you're going to do your oil changes based on condition, right, then yes, maybe there could be logic to switch to synthetic that arguably should last longer. And I only qualify that statement by saying as long as it's the condition of the fluid that causes the oil change and not contamination of the fluid, because to be honest, mineral oil and synthetic oil contaminate at the same rates. So yeah, very loaded question. You would need to present more data to see if what the answer might be. But short answer is not necessarily would you make that recommendation quickly. It's based on more factors.
Thank you. Another question we have is, if the existing sample point is not representative, should the equipment continue to be sampled, or should they hold off on sampling until the sampling port has been modified?
I would say no, that you might as well continue sampling even from the less representative sample point, because anything that's consistently done still provides you with some indication of what's going on. While it may not be the most representative point, at least if there was a significant change within the system, you should still be able to detect it. So I wouldn't stop sampling and wait until you have, the problem we call is waiting for perfection, because perfection never comes. If you decide to stop doing anything simply because you don't think you're doing it as best as possible, you're not really advancing, you're not moving forward. So I would say no, continue doing it the less optimal way until such time as you can make the change.
Great. And then I have one more question for us for this time. And when you were discussing the ROI early on in the presentation, was that ROI representative of on-site oil analysis or using an independent laboratory?
Any. The ROI can be, like I said, anywhere from 2.5 times to 20 times are most of the examples you'll come across. And they range dealing from any of the 4 laboratory choices of OEM, supplier, independent commercial, or in-house. There's always a savings. And the point is oil analysis, vibration, thermography, and infrared, any of the 4 technologies, when done right, they all pay for themselves. So it doesn't matter who you contract it to, you should be able to get some type of savings out of it. How much savings you get doesn't really matter with who you've dealt with. It's more how well implemented it is, and kind of how bad things were before you got started.
Hmm. Thank you, Evan. So I think that's all the time that we have for questions at this moment. And I know we have a couple more that were not answered. Evan will be getting to those later today. And if you do have any other questions that you think of later on, or you need any sort of assistance, please feel free to get in touch with Evan. His email address is there on the screen. And if you have any other information you're looking for, you can always search testoil.com. We have plenty of ebooks, on-demand webinars, and upcoming training classes listed on the website for your perusal. On that note, Evan, thank you very much for your time and sharing your knowledge.
All right, thank you.
All right, everyone take care.